Yes.
I'm going to
Yes.
put this in. Okie dokie. Can you guys, is it in full view for you?
Yes.
Yes.
Okay, good. Okay, excellent. So thank you all very much. And Marcia, thank you for inviting me to talk with you all this evening. We're really excited at Fulcrum about a biomarker that we've been working on. We've been working on a whole body musculoskeletal MRI protocol in order to quantify and evaluate muscles in the whole body. And so I know that this is a big title, but really what it is, it's just talking about our MRI protocol and how we have advanced the current MRI technology for evaluation of muscles, especially in patients with FSHD. And so, let's see if I can advance here. These are just my disclosures. I just wanted to just tell everybody, and I know that everybody is aware that we have completed the placebo-controlled portion of the REDUX4 clinical trial. However, I can't take any questions related to that. So we'll just have to focus on MRI for tonight. So why whole body musculoskeletal MRI? And it's so important because they're really, when you think about how we evaluate people with muscular dystrophies, I know that all of you have been evaluated by several different physicians. It's really, you can only concentrate with clinical outcome assessments at one body part at a time. There's really no, a sort of 6-minute walk test or tug test where you're getting up from a chair, walking 6 meters, coming back down. That really assesses the whole body and gives you a sort of a holistic view of how all the muscles are doing in your body. And so MRI, regardless of whether you can do those evaluations, whether you can stand up and walk or use your arms, can be done. And it's so important for us to develop this technology because really this whole body musculoskeletal MRI, as I said, captures the holistic evaluation of all of our muscles, upper extremity, lower extremity, and trunk, all of which are affected in FSHD. And also, what's not necessarily unique to FSHD, but really challenging for patients with muscular dystrophy is that not all muscles are affected equally. So it really gives you an idea of how muscles are affected in each patient. You can capture that. And you can see here that there are 3 different patients that I'm showing here. Can everybody see my pointer? 3 different patients showing here, and they all have very different muscles that are affected. And so, but we can now capture that and understand which muscles are effective. As I said previously, it's non-invasive and really minimal burden on patient participation. Most of you or some of you may have had an MRI in the past. I've had an MRI in the past and I thought this is going to be no problem. But I pressed the button after 2 minutes, which I was really surprised about. But people tend to tolerate them now better. And it actually can be quite comfortable in the MRI. You can watch movies and listen to music, and most MRIs usually take under an hour, so you can actually participate. And the other reason why we're so interested in MRI and muscles is because unlike the clinical outcome assessments, which can sometimes take a long time to detect changes in, the MRI can actually detect changes prior to you even having some difficulties or noticing those difficulties. So Krishna, I was really struck by your story is that you never had any issues until you were 60 years old. And perhaps maybe if you had an MRI prior to this, you might have seen some of the changes in your muscles prior to the point where you started having difficulty or falling or something like that. And so I think that, so we believe that MRI likely detects these changes before actually the clinical outcome assessments change, before people start falling down or start slowing down in their walking. And by the way, this talk should be interactive. So if there's anything that anybody doesn't understand or wants me to discuss further, please interrupt me. This is a really nice, intimate group. So I'm really excited to actually give this talk in this forum and get your feedback in real time, so you don't have to wait until I'm finished. So I just wanted to provide some definitions for everybody, since MRI may not necessarily be as familiar to you. When we talk about MRI, what we're talking about is magnetic resonance imaging. And this is really, again, a non-invasive imaging that is based on magnetic fields of hydrogen atoms in the body. So there's no radiation in MRI. And also with musculoskeletal MRI, or at least in our protocol, we are not using any sort of contrast agents, gadolinium or anything like that. We can actually use different, what are called sequences, and I'll go through that in a minute. And these MRIs actually come in different strengths. So you might hear about, 1.5 Tesla MRIs or 3 Tesla MRIs, and this just denotes the strength of the magnet. So, and it really, the higher the strength of the magnet, the better the picture is. Actually. So a 3 Tesla or a 3T MRI gives much better pictures than a 1.5 T Tesla. And a 7 Tesla, if you're around that, just make sure you park your car far away, or else it can be, brought in or taken off the road by the magnet if you're around a 7 Tesla. No, just kidding. They're actually shielded. So you should be fine if you park a little, maybe a block away. And never bring your credit cards in, because the magnetic strip will be completely erased. So, and then you won't be able to spend money, which probably for my husband would be a good thing for me. And so there are different ways in which we can look at the images on the MRI. So we talk about 2D or 2-dimensional MRI, in which MRI images are there like slices. So we take slices through the body to look at the different tissues, or they can be 3D, in which we can take different pictures together, and we do fancy calculations to actually create 3D pictures of what your body looks like on the inside, or whatever. In this case, we're interested in our muscles, what our muscles look like in a 3D image. And how we do this is it can be done by using what's called 2-point, 3-point, or 6-point. And what that means is it just refers to how many images we are using to create either these 2D images or these 3D images. So you might hear some of this technology if you have an MRI, or if you're looking at different papers or hearing different scientific talks. And as I said, did somebody have a question? Okay. Like I said, if you have a question, please feel free to interrupt me. So like I said, we don't use any contrast in our protocol. What we do is we try to take advantage of, and what a lot of muscle MRI protocols try to take advantage of, is what we call different sequences. So, and how we do these different sequences are different ways in which we manipulate those hydrogen atoms, if you will, in your body. And so you might hear the phrase T1 weighted images, and these T1 weighted images actually give us a great idea of what anatomy looks like. They give really nice pictures of what normal anatomy looks like, whereas what we call T2 images give us an idea of pathology. And so things that look pathological are usually white or bright on the MRI. And so sometimes, for instance, in FSHD, we see some of the muscles don't necessarily look normal, because they have a white or a bright signal in them, which can signify either swelling or edema, or perhaps even fibrosis or replacement of the muscle by fat. We also use a sequence called STIR, or short tau inversion recovery. You can just say STIR image. And again, this is another way for us to manipulate the hydrogen atoms in your body to let us know if we're looking at other pathologies. However, one of the most popular sequences to be used, and you might have heard about this and thinking about MRI and looking at different MRIs, is something called the Dixon sequence. And this Dixon sequence allows us to calculate different quantitative measures of muscle health on the MRI. So some of you may have heard of muscle fat fraction, especially in the Duchenne space. And these are just quantifiable measures of fat, how much fat is in your muscle. And how we do that, how we calculate that, is by using this Dixon sequence. And this fat. So the more fat that's in your muscle, the less healthy your muscle is. So by being able to evaluate how much fat is within the muscle gives us an idea of how healthy your muscle is. And this has been looked at in several different muscular dystrophies, as well as other neuromuscular diseases, and also in FSHD. And there's another, MR spectroscopy is another modality. It's a little bit different. It uses mathematical sequences to determine fat and water content. We won't talk about that today, but that's sort of the gold standard to which MRI sequences are held to. So I talked a little bit about the quantitative measurement of muscles and muscle health. So, and I talked a little bit about fat, but one of the other types of measurements that we use for muscle health. Yep.
Excuse me?
Yes.
Based on what you say, does that mean the lesser the fat in muscles, it is less prone to degeneration, or is it good or bad for having less fat?
Yeah, so having fat in muscles, the more fat, the less healthy the muscle is, or the sicker the muscle is.
Oh,
so you don't want fat in your muscles.
Oh.
Certainly, as we all age, we all naturally accumulate some fat in our muscles, but people with muscular dystrophies, their muscles can sometimes be completely fat replaced, and that's what causes the weakness in many muscular dystrophies. So for example, in FSHD, it's not uncommon, even if people aren't very impaired, for their hamstrings, the muscles in the back of your thighs, to be completely fat replaced very early on in the disease. The nice thing is that, you know, as humans, we're very adaptable. So we use different muscles, but as the muscles become more and more fat replaced, and as you've experienced, Krishna, you know, you have more and more difficulty walking, and it means when you have all this fat, that's what causes the muscles to be not healthy and not function appropriately.
Why I was asking is that when I didn't, I knew because of my blood test that I have what they call it one gene, DHX4 or
DUX4.
yeah, and it has a less what you call I don't know the technical name, but it used to be there are two pairs each gene. They should be equal, and I have got one gene where that other R and S or whatever, that other number, instead of having 4524 or something like that, I don't have that report with me. I had instead of 4524, I had, I think, 45 less than 24 or whatever, and that I was told that gene expert that one gene is causing all this FSHD.
Yep,
so
that's correct. Yes.
So what I was during my professional career, I was little, obese, little fat because of a lot of eating this and that and not taking care of. Does that, because of that, at the age of 66, I started showing FSHD, that kind of fatness has a relation with what you are saying?
So actually body weight does not have a correlation with FSHD. It's actually the fat in the muscle and the accumulation in the muscle. So body weight, and while it's better when you're weaker to not carry extra weight, because then you need more strength to carry that weight around, it does not necessarily correlate per se with the onset of FSHD. And what you had talked about related to the genetics of the DUX4 gene, it's true that the shortening of those repeats that is the architectural plans for DUX4 is what is in our DNA is what allows DUX4 to be expressed, and that's toxic to the muscle. And because DUX4 is toxic to the muscle, what happens is that the muscle gets sick, and then the muscle is sick, and then because it's sick, it gets replaced by fat. Those muscle fibers can't function appropriately, and they break down, and then fat, there's some inflammation there, and then fat comes in and replaces it eventually. So it's not necessarily having to do with your body mass index or something like that.
Thank you.
You're welcome. So other than measuring fat, one of the other quantifiable measures that we look at is something called lean muscle volume. And so what I'm showing here is that the lean muscle volume is looking at that muscle that is actually functional. So obviously you want a lot of lean muscle volume. That's normal for your age because this is your functional tissue. And so what we're showing here is we're showing the leg, the upper thigh actually, and these are your quadriceps. And basically here you can see in red all of this nice muscle. This is a nice looking muscle. You like all of this muscle. Here behind here, this is your adductor magnus, and these are your hamstring muscles. You can see here that there is not as much red. There's a little bit more white, and that white is actually fat that's inside the muscle. So I would say here your quadriceps actually in this patient actually look pretty good, but here in the posterior part of the leg here, your adductor muscle here, as well as your hamstring muscles are looking a little bit less healthy because they have some of this white in it. And here it's colored. It doesn't necessarily look like this on the MRI. This is the top here is the MRI image, and you can see here that these white areas, these bright areas, are what is not normal for muscle. And so, this lean muscle volume tells us how much functioning tissue you have. Whereas when you're taking a look at the muscle of the fat, like within the muscle, so this is something called muscle fat infiltration. And this is what I was talking about, looking at that fat within the muscle, and that this fat within the muscle is actually making these muscles sick and not being able to function as well. So the more fat that you have within the muscle, the less healthy your muscle is. And looking at the fat within the muscle itself, within that part of the muscle that is functioning really well, could potentially be an early indicator of muscle health, of that muscle getting a bit thicker. And then we also have something called muscle fat fraction, which some of you may be familiar with and reading about that in literature. And that's really looking at the amount of fat inside the muscle as well as outside of the muscle. And so that gives us an idea, another measurement of how healthy that muscle is. So we have several measures, quantitative measures on MRI. This is all calculated by computers for us and standardized. And so we can get a really nice idea of how much functional muscle there is and how sick muscles are as well. And we can look at each muscle individually. And when you take a look here and you're looking at the muscles, you can see here that these muscles for here, we're looking at your back muscles here. On this MRI, you're looking at a shoulder muscle here, and you're looking at a leg muscle here. These are what normal muscles look like. And we can really see, when somebody's gone in and outlined this for us, but you can really see how nicely we can really take a look at these muscles. and really delineate them. But as more of the white comes in or the fat comes in, it becomes harder and harder to really tell the difference between these muscles and to identify the individual muscles. And so this could be one of the issues that comes up, especially in FSHD, of being able to evaluate muscles on MRI. But for the most part, we are able to identify them pretty well. And so when we started our study, what we were trying to do was develop a whole body protocol and analysis to look at muscles in their entirety. And we really wanted to generate a composite measurement that correlates with clinical outcome measures. And the reason why it's so important to correlate your MRI measure with a clinical measure is because it gives us meaning. Like, you know, then we can say, okay, if your left leg is weak and we know that these muscles are affected, and we can say that you're not going to do well on certain clinical outcome measures like the tug, or it's going to affect your walking. And so it's really important for us to make those connections and those correlations to give it meaningfulness. And what's new about our evaluation of muscles within the body is that what people usually do right now is they just look at the leg muscles. So for many people who currently don't have use of their lower limbs and have more use of their upper limbs, we haven't really been able up until this point to look at upper limbs. And so with our protocol, we're able to evaluate upper and lower extremities. And unlike the usual protocols where we just take samples, if you will, of the muscle. So you just take some samples of the muscle. We are able to look at the whole muscle in its entirety. And we are also able to use, so what we usually do, or what I did when I was a resident, is we used to lock residents in basements to outline those muscles, to read them. So somebody has to go in and actually draw these circles around the muscles to delineate them so that they can be analyzed. But what we did with our partner AMRA was we developed an automated system so a computer can actually do it for us. And then somebody can go in and make sure that the computer identified those muscles appropriately, so that when the computer identifies a thigh muscle, that we know it's a thigh muscle that we're looking at and measuring. Also, because we are looking at muscles in their entirety, we're able to look at the volume of the muscles and really take a look at the muscle health. And we're also able to look at these muscles in 3D rather than just in two-dimensional. So we really get a really good idea of what the whole body looks like, not just taking a sampling of the lower extremities and extrapolating from the lower extremities what the rest of the body may look like. Because as you all know, not everybody's affected equally. And as I said, for most muscular dystrophies, the different muscles are affected at different times in different people. And so this really enables us to also think about on an individual basis and follow in patients on an individual basis those muscles that are affected, or identify those muscles at risk for becoming weaker. And so again, as I said, so usually what we have done in the past was look at these single slices or select slices of muscles in the lower limbs. But with our new technology, we're able to actually, instead of just looking at these slices, we're able to look at the muscles, and I'll play this little movie here. We're able to look at the muscles in their entirety, from top to bottom, and able to also take a look at, and you can see here, all of the different sequences and the different images from each muscle, and not just at these single slices. And this really gives us an idea of what muscles to follow in patients over time. So this is sort of an individual basis, individualized medicine in which we can say, okay, we know that these muscles are at risk or weak or normal, and we're going to choose a specific set of muscles to follow and see if they respond to treatments or therapies. And so the study that we designed was done at 6 sites in the United States and 1 in the Netherlands. And we actually did this MRI protocol on 17 patients. The MRI was done when they came in first to see us, and then we did another one 12 weeks later, because the reason why we had to do 2 in such a short period of time is we wanted to make sure that what we were measuring was actually what we were measuring, and that the measurement of what we were taking was stable. So it's really important to make sure that the measurements that you take are the same at time point 1 and time point 2, because it speaks to the stableness of that measure. We also did muscle biopsies in this patient population, and part of the reason why we did the biopsies is because for our studies, we wanted to identify the DUX4 signature so that we can follow that over time. And we had talked about that at a later time, or we can I can answer some questions about that later. I didn't go into it in this talk, but I think some of you might have seen that data previously. And also what we did with this MRI protocol is we looked to correlate our findings on the MRI with our clinical outcome assessments in these patients that were taken at the time. So we had them do this, I have here TUG, which means timed up and go. So what happens is you guys start in a sitting position, and we start a stopwatch. You stand up, you walk 3 meters, you walk around a cone, you go back to the chair and sit down, and we stop the stopwatch, and we do that once or twice to time that. Fulcrum also developed something called the FSHD TUG, because we had heard from you that one of the biggest concerns was the weakness you have in your trunk, and people had told us that you had a lot of difficulty getting out of bed. And so we added this supine to sit, or laying to sitting, to the TUG to try to capture or see if we can evaluate that trunkal weakness. And then we also added another measure. So not only looking at these walking measures, which can potentially exclude a lot of people from clinical trials because they can't walk or have lost the ability to walk, we also included an upper extremity measurement, something called reachable workspace, where you actually sit in a chair in front of a screen like we are right now, and you follow the person on the screen moving your arm, and we measure with something called a Connect device. I don't know if you guys have kids or have played with this yourself. Microsoft, I think it was like in the 90s, had developed the Connect for video games, but Jay Han and his group at University of California, Irvine, have adapted it to be able to evaluate how much space people can move their arms. So we can actually measure with this device, and here what we're showing is the measurement of how this person can move their arm in space. And we divide it up into 4 quadrants in order to make our measurements of the area that you're able to cover with the movements of your arm. And we included people with FSHD that were 18 to 65 and had a confirmed diagnosis of FSHD1, as well as a clinical severity score of 2 to 4. So in this case, people had to be able to walk. And because we were including a muscle biopsy in this study, they also had to have a leg muscle eligible to biopsy and have the presence of what we talked about the STIR imaging. So the Wellstone group previously had done a study and had found that looking for this abnormal signal in muscles loosely correlated with the potential, an increased potential to detect DUX4 in that muscle. And hence the reason why we required that for people participating in our study. And for this study, the average age was 49, about 30% were female. People had an average severity score of 3, which means that they could walk, but may have had a little difficulty. And the average number of repeats, which Krishna was talking about, that he had the short number of repeats, was about 5.2 repeats. And when you do the protocol in this study, so each person underwent the protocol, they had all of the images that we had talked about. You lay in the scanner and we scan your neck, your torso, and your legs. We lay these mats over you so that we can look at your muscles. And then we have you shimmy over to one side of this is the magnet here. This is the bed. This is you or another patient laying on the bed, and we lay you first in the center of the magnet. And you go in and we image your trunk to your legs, and then we have you shimmy over to one side. So now your arm is in the center of the magnet, so we can get good pictures of your arm. And then shimmy over to the other side so that we can get pictures of the other arm. And the total exam time here is really about 30 minutes.
Michelle, this is Lee.
Yep.
I think you just answered my question, but is it standard MRI machinery or does it require different equipment? It sounds like you're just using standard machine.
It is, yep, that's a great question, Lee. Yep, we're using a standard machine. What's different is the software that we use to analyze the data that's collected by the machines. Most MRI machines, so most hospitals have Siemens or Philips, are compatible with this software. The only software we were having difficulty with at the time was the GE software, but EMRA has worked on that and has fixed that issue. So we can pretty much go into any MRI center, and do this protocol. So it doesn't necessarily require you getting a 7 Tesla MRI. One thing is that it works better on the 3 Tesla, so that one MRI that gives you better pictures than that 1.5 Tesla. But most centers today have a 3.
Thank you.
You're welcome. And with our MRI protocol, we're able to look at 18 muscles bilaterally, so for a total of 36. So we look at muscles in the shoulder and in the neck, these muscles over here, and these muscles actually tend to not be affected by FSHD. And so these were sort of our internal controls to be sure that we were measuring what we thought we were measuring, and weren't getting any weird signals from our protocol. And then we also looked at the torso here. You can see here the pecs, the rhomboids, your trapezius is here in red, the serratus, which is actually in the back, and that holds your scapula actually to your back. And then the legs, you can see here, we also imaged your legs as well as the arms. And those muscles that are in orange and red are more affected than those muscles that are in yellow and green here. And that's what this image is showing. And so what we do is we take the images. So these are images that are taken by that. So you can see here that we can go back here from these images here. We take your images, and this is somebody, this is their pelvis, their upper leg, this is their mid leg, well, this is their thigh area, this is your knees, this is your lower legs, and you can see their feet here. And actually we calibrate these images and then stitch them together. So essentially there's no missing data here. And then what we do is we take these images and we basically send them to the computer and tell the computer, we say, identify all the muscles for me. We tell them which muscles to identify, and that's what these colors are showing here, are the different muscles of the thighs. So here's your quadriceps, your adductors, here, your hamstrings here, is what's being shown in these different colors. And somebody also goes back and takes a look at this to make sure that the machine is actually doing its job appropriately. And then what we do is that we take the measurements that we talked about. So we can have the software compute for us how much lean muscle volume you have. And this lean muscle volume is how much functional tissue there is. And we can also look at that muscle fat infiltration, which basically is looking at how much fat is within that functional tissue, giving us an idea of how sick that muscle may be, as well as the muscle fat fraction, which basically takes a look at the fat within the muscle as well as outside of the muscle here. And that gives us an idea also of muscle health as well. So we're taking several different measurements to inform us of how healthy your muscles are. And we can follow these quantitative measurements over time. So the higher the fat, again, the more sick the muscles are. The higher the lean muscle volume, the more healthy the muscles are. So usually when fat goes up, the lean muscle volume goes down, and vice versa. And we've also been able to classify these muscles based on these quantitative measurements. And these are based on literature assessments and our own experience, where we were able to identify normal muscles that appear unaffected by disease. We identified muscles that were most likely to progress. And again, it's based on the measurements that we did of the muscle health, and identify those muscles that are end stage, those muscles that are unlikely to be, may not be responsive to treatments. And we looked at these muscles in all of the patients in our study. And as you can see here, all the patients in our study had a mix of muscles that were healthy, as well as likely to progress, and also end stage. And this also, I think that this is a really nice picture, because it speaks to how the heterogeneity of the disease across this population, which we tried to make as similar as possible, because that's what you do in clinical studies. You try to make people as similar as possible. But you can even see, even though we work to try to make people as similar as possible and have these strict criteria, that there's still a significant amount of heterogeneity between patients. The nice thing about this was that we were able to evaluate 478 muscles out of 612 muscles. And the nice thing about looking at muscles on a muscle by muscle basis rather than on a per patient basis is that your number, when you're looking for, a potential effect of treatment or how things might be progressing, is now expanded exponentially. So even though we had only 17 patients in our study, we were able to evaluate 478 muscles, which is a lot of data, and gave us a very nice idea of how we can evaluate muscles over time in patients with FSHD. We did have some issues, and no protocol is perfect, and had to exclude some muscles. As you can see here, we had some technical issues, had to exclude 64 for that, and we also had to exclude 70 muscles because they were completely fat replaced. And like I said, when muscles are completely fat replaced, we have difficulty drawing those circles around those muscles and identifying those muscles. And I think that I actually really like this picture because it shows how the whole body musculoskeletal MRI can really be, can individualize each person, not only on a person by person basis, but also give us an idea on a muscle by muscle basis of how things are progressing in patients and in the population of muscles that we're looking at. So each of these figures here is one of the patients in our study. These are the different Ritchie scores. The Ritchie scores are our clinical severity scores, where lower scores are less severe and higher scores mean that you're more severely affected. And you can see here that, even though somebody might be less affected, they still have a significant number of muscles, or the pattern of their muscle involvement may be different or even the same as somebody that has a Ritchie score of 4, but because the clinical severity score is based on our clinical assessment, we may not necessarily capture that. Whereas here with the MRI, we can really understand on a muscle by muscle basis how the disease is affecting you, at least on that level, at least on that muscular level. Are there any questions here?
Yes, that you few times stated that under certain conditions or when fat level is high, that the treatments may not be will not work, or that cannot be treated. What kind of treatment? I thought there is no treatment available for degenerated muscles.
Right. So that's currently what people like myself and Julie and Fran are currently working on, is we're trying to work on treatments for these degenerated muscles. Now, it sort of depends potentially on how severely that muscle is affected and the type of treatment you might be looking at. So a muscle that's severely affected may not be responsive to one type of treatment, like let's say an anti-inflammatory or other types of treatment, but may be responsive to a treatment that helps that muscle regrow, something like myostatin. So I think all muscles are potentially amenable to treatment across the spectrum. It just depends on what the treatment is and how that treatment is going at trying to help that sick muscle. So it goes to how that treatment is going to work. So there, as I said, there's one treatment called myostatin, which helps muscles to regrow or get bigger. So that can help maybe muscles that are more severely affected, or help those healthy muscles compensate for the severely affected muscles. It's hard to say, and hence the reason why we have to do clinical trials, but also understand how muscles are affected in each person's body, so that we can understand or predict or correlate what we're seeing structurally with what we're seeing in the clinic. You know, how you're doing on a 6-minute walk test, or even that reachable workspace test that I had talked about.
So the patient you have to evaluate patient in your clinic with a different test before you can suggest any kind of treatment.
Well, in the future, I hope that I will have that opportunity to be able to look at patients on this individualized level and say, okay, I have this arsenal of treatments to potentially choose from to give you, depending on what I see, potentially on MRIs or my clinical outcome assessments. And that's the type of research I believe that the FSHD Society, Mark and Jamshid and ourselves are trying to, that's the place we're trying to get to.
I was going to ask just what's, oh, sorry, go ahead. Sorry.
No, so for example, this Rush Medical Center, that, I have a FSHD neurologist. If I talk to her, she hasn't, we haven't talked about treatment at all. So I'm completely under the impression that there is no treatment available. Of course, I know the research is going on and some work is being done, like you are saying. But I was completely under the impression there is absolutely zero treatment available.
So Krishna, your doctor is currently correct. Unfortunately, at this time, there are no approved treatments or disease modifying treatments for FSHD. there are, I'm sure as you're aware, supportive treatments, which are, working, doing the scapular surgery or using canes or wheelchairs. But you're absolutely right. At this time, there are no approved treatments. But in order for us to get to approved treatments, we need to be able to measure how our proposed treatments are going to affect those diseased muscles in your body. And up until this point, clinical outcome assessments, looking at how you walk, looking at how you reach for things, change very slowly. And so the whole idea behind this is to try to find something that changes or will show changes more quickly or in a shorter period of time, so that we know how to evaluate patients and how to treat them, as well as assess the effectiveness of treatments for patients.
So, what you are saying, there is no treatment, but there are excuse me, there is what is available. I could not get it.
No, I'm not saying that. What I'm saying is that we're working on it, and we're hoping, as Bill said earlier, we're hoping to have a treatment available to you by 2025.
Oh, okay.
I was going to ask Michelle, what's next for this? So I'm just thinking practical application, and to me, and I'm a novice and I know nothing. So I'll say that I know nothing, but it seems to me like if this was proven, it looks like if this was applied more widely and more people were using it, that it could stand to speed up the research process, because it allows you to show efficacy in a clearer way.
Yep.
Is that
That's
correct?
right.
Okay. So then what's next? Where do we go with this technology and utilization next?
Yep. So you're exactly right, Lee. So where we've gone next with this is that we are using it in our phase 2 clinical trials. This was sort of the basis for being able to include this protocol in our phase 2 clinical trials, where we're looking at where we're looking or evaluating the potential of losmapimod to treat FSHD. So this is one of the biomarkers, if you will, that is included in our phase 2 clinical trial.
Do you see this eventually being used in the clinical setting? Not in a trial setting, but
right. Marcia, it's possible. I think because it is so widely applicable, I think that in the future, if there is a way to say, okay, we need this MRI in order to make informed decisions for treatment for patients with neuromuscular diseases, FSHD, possibly Duchenne, other things like that, I think that it could potentially be used in the clinic to help make those decisions.
just this slide that you have up, I mean, there's just so much individual information on that slide.
Yeah.
That in a clinical setting could be helpful.
Absolutely. And I think that that's the point, is to be able to understand not only on I'm walking better, I'm feeling better, but also showing that yes, there's also a structural benefit to being on a treatment.
I have a quick question.
Yes.
I have two actual questions. So first of all, I have a smart scale that shows body fat percentage, and I know that's not a super accurate number. But when I look at mine and look at what the appropriate number should be, my body fat is probably twice what the appropriate number should be for a healthy person. And I'm a little overweight, but I'm not like a severely obese person, but my percent of body fat is, close to 50%. So do you think that the reason mine is high like that is because of my affected muscles? And I know, it's not necessarily accurate, but I mean, could that be a reason for that?
So it's a different type of a measurement that you're looking at. I'm assuming that with this SMART scale, it's a body mass index type of measurement. These measurements are very specific to being measured by the MRI and specific for muscle health, and does not, and while some may actually contribute to that, I would say that it's on a different spectrum. It's measuring something different.
Okay, that's fine. And then the other question is, I'm doing physical therapy because my physical therapist is a neurological physical therapist, and she's trying to help me, with balance and with some range of motion and other things like that. And I feel like I have improved by doing that. And, I'm 60 years old, and I wish that would have been something suggested to me when I was 40, when I was diagnosed.
Right.
Would something like this be helpful in treating patients and saying, okay, we see that, these certain muscles are weaker. So can we do something to maybe do some physical therapy that will help you maintain your mobility by, maybe we can't strengthen the ones that are severely affected, but maybe we can help strengthen the other ones, the surrounding ones, that would help, continue, with having more strength and a more productive lifestyle.
Yep, absolutely. So muscle exercise has been shown to keep people mobile, and so yes, and that can be potentially shown on MRI with changes in muscle. Probably lean muscle volume would be my guess. Sort of like a weightlifter or a bodybuilder, you might see a little bit of an increase in the lean muscle volume, and so that might be something that would change. But certainly, exercise has been shown to be beneficial for patients with FSHD. I'm not saying that you have to go out and bench press or start powerlifting or anything. I would not recommend that, but certainly light aerobic exercise is certainly beneficial. Absolutely.
Yeah. I mean, and that's kind of, in my opinion, that when I was first diagnosed, and I said, is there any exercise, physical therapy things I can do? And my neurologist is like, no, nothing you can do. You're just
Mary, you're not alone in that. We hear that over and over and over again. But the FSHD Society actually has a lot of exercise videos that are specific to those with FSHD. It's a trainer and a patient and a physical therapist that have put all these together, and they're on the YouTube channel. And everyone that's been utilizing them has had a lot of positive things to say about the impacts they're having, the effect they're having.
Okay.
Yeah. And there's also a lot of mental health benefits too, from movement and just being able to, move your body and exercise. There's a lot of also mental health benefits to that as well.
Yeah. Thank you.
Great.
Which YouTube channel they have that exercises?
Lee, which YouTube channel is that for the exercises?
Sorry, I was muted. It's, if you go to the FSHD Society website and click on FSHD University, Living with FSHD, I'm going to drop the link in the chat. And Marcia, why don't we do a follow-up email?
I was planning to, yes.
Yeah, and we can share that link. I'm having trouble copying it right now. Hang on one sec, and I'll drop it in the chat. But it's the FSHD Society's YouTube channel, and you can also get there from the FSHD Society's website, which is fshdsociety.org. and you would just go to, there's a section that's called FSHD University that's highlighted on the front page. That's going to be the fastest route to get there.
Okay, thank you so much.
Absolutely.
Yep. So I'm going to just show you one last thing, because I know that we're starting to run late on time, Marcia, and I know that you said that you had other business as well to.
Just a few little things, and I can actually add it mostly to the follow-up summary.
Oh,
email,
great.
so.
Okay. I just wanted to just briefly talk about, because we talked about these 3 assessments, these clinical outcome assessments that we did for this study. And we worked with a physical therapist to identify those muscles that are most involved with each of these clinical outcome assessments that we're looking at here. So with the FSHD tug, like I said, where you start from laying down to sitting up, we're assessing your trunk muscles, we're assessing your walking muscles, probably a little bit of your arms. Whereas with the tug where you're just sitting, it's really just your legs. And with the reachable workspace, we're looking at your arms. What we did was that we wanted to, we developed these composite scores where we just looked at those muscles and wanted to see how that correlated with what we were getting in the clinical outcome assessment. Like how did that look? And so what we found was that when we looked at it, so here is and this might be, a little confusing. I know that there's a lot of detail in here, so I'll walk through it slowly. But so what we did was we looked at the muscle fat fraction of those. We took one of those health measures, those muscle health measures, that being the fat fraction here, and we looked at how long it took. We looked at how long it took for patients to complete that tug study. And what we found was that the longer it took for people to complete that tug, the higher the fat fraction. So there was actually a very nice correlation with the sicker your muscle is, muscles, I should say in this case, sicker your muscles are, the longer it takes to do the tug. And we also saw that in that other fat measurement, that fat infiltration measurement, the same thing. The higher that, the more fat you have in that contractile portion, in that functional area of your muscle, the longer it's going to take for you to finish that tug. And we also saw some similar results with that FSHD tug, the one where you start from lying down, where the thicker your muscle is here, the longer it takes for you to complete that tug. And you see the same thing in that other fat measurement here, as well as you see here, when you look at the reachable workspace, again, you see the sicker your muscle is, the least amount of space that you can actually use your arms, the lesser amount of the space that you can use your arms. And this is for the left arm and the right arm, and you can see that on both measurements here. So with this information in hand, and by looking at this study, and with patients such as yourselves volunteering your time to be part of this study, we were able to develop this new protocol, this whole body musculoskeletal MRI protocol that looks at muscles in your arms, your trunks, your legs, looks at the entirety of the muscle, does not necessarily just take samples of the muscle. And we were able to show that that you all were able to, or the patients in the study were able to tolerate, most importantly, we're able to tolerate having the MRI much better than I ever would. The measurements we were taking were actually good measurements and gave us a good idea of the health of muscles, and that actually the measurements that we're taking are meaningful because they correlate with what we call clinical outcome assessments or functional assessments that tell us how well you function over time. And so we think that the musculoskeletal MRI, this whole body protocol, will be really helpful in capturing disease heterogeneity over time and provide you, patients, and your families with information about disease severity, and also be able to help us understand changes in those functional assessments that you have. So I just want to just take also a moment here, and I'm happy to stay on and answer more questions, but just to thank really the patients, you all, for providing your time and effort and your commitment to all of our studies. I through this pandemic, I've just been humbled by your commitment to our studies and really hanging in there with us, not only with this study, but with all of our phase 2 studies. It really has been wonderful to continue to work with this community, and I look forward to sharing more data with you all in the coming months.
Thank you
Hi,
very
Michelle.
much.
Hey, Fran.
Michelle, can I? I'm sorry. Go ahead.
One question. Thank you very much. That was very nice. You mentioned the yellow muscles that are more likely to progress.
Mm-hmm.
And I'm wondering, throughout your studies, if you figured out how fast the muscles are progressing, and that if you had a certain number of patients, would you be able to tell in a clinical trial setting if a drug was preventing progression of disease?
Yeah, no, that's a great question, Fran. We actually did look at that, and we were able to show that those yellow muscles do in fact progress faster than the green muscles, and also the red muscles, because the red muscles are end stage, the green muscles are normal. We know from prior studies that the progression rate is between like 3 and 6% for those yellow muscles, and when we looked at that, we were on the same range there for what we could predict would be that annual progression, and part of the reason why we wanted to identify these muscles, Fran, or those that are most likely to progress, is because we were trying to enrich that population of muscles that are going to show change over the time period of the clinical trial.
Thank you.
This is great data. Thank you so much, Michelle. This is Jamshid. Quick question. So for a biomarker to be accepted, the regulatory agencies have to buy into it. And what are the next steps that have to happen for them to see this?
Right. Yeah. No, I think part of it, you're absolutely right. And Jamshid, I know that you and I in June had talked previously about CPATH and talking about accessing the pathways through there. And so we're working with AMRA and thinking about the best path forward for that, and thinking about potentially engaging with CPATH to help us qualify this measure.
Okay, I wasn't aware that they were able to do that. We just had a chat with them.
Yeah, I think that they have a similar working group with Duchenne.
Chance,
and
okay.
so it'd be great for them for us to also be able to do something similar. We might not necessarily be able to, I don't know if I brought this up with you. I mean, it would be great for us because there are so many protocols and so many people working on trying to understand the best way to measure muscle health in patients with FSHD, and it's so heterogeneous that it might be helpful to, as they did with the ADNI data set, for us to develop a standardized protocol or work with other companies with Fran and Ultragenics and things like that, and trying to come up with a standardized protocol for FSHD.
Oh, that'd be great.
Yeah.
Wonderful.
Is this technology proprietary to Fulcrum, or is it available to anyone who is going to pursue a trial?
So the technology itself, Bill, is available on all MRI machines. It's actually the software used to analyze the data. And so that software is proprietary to AMRA, actually. So the idea is for AMRA, that people can collect the MRIs on whatever machine, make sure they do it consistent with what is needed for this analysis. And then AMRA can essentially license the software to that person, or AMRA themselves can analyze the data for you so that you can get these measurements.
So it'd be kind of software as a service.
Exactly. Yeah.
Okay.
Yeah, because AMRA is essentially a software company, so they've developed this software to be able to do this.
Thank you.
Other questions? So I just want to say, I think that this is a very exciting time for patients with FSHD. The FSHD Society has certainly been leading the way and breaking new ground for our community. And like I said, I'm really looking forward to sharing more data with you in the near future. I know that you all have a conference coming up in June, and so so we're looking forward to seeing you all there and continuing this interaction and discussion.
Thank you very
so
much. Yes, this was great. We appreciate your time. Very informative. Thank you.
Thank you, everybody.